we ourselves, as Dave will point out, have been to guarantee that portability working on the 386-46 instruction set on this instruction set. We also did an early port to the 860 that allowed that port to basically stop, given the problems that there were with the 860 chip.
So that defines the bounds of reasonableness.
Yeah, certainly we would consider, the following to be reasonable machines: RS-6000, SPAR, Motorola 88,000. An unreasonable machine might be a Cray, although you probably port to that and just take a lot more work. But the goal is that, as Dave will explain later, to make it fairly easy to port to a reasonable architecture. So that's basically our strategy. What Dave is going to do is basically go through the high-end technology, in particular focusing on the foundation layer. This is a layered system, so you basically have a foundation and you extend it by adding subsystems to tailor for a particular programming environment or function. Why don't I, before we go around and introduce ourselves, let me introduce Dave Cutler. Dave's been with us 2.5 years.
Yeah.
Dave used to be digital equipment before Microsoft, and has been with us for 2.5 years, and basically is the godfather of this technology and has all the developers working for him. Introduce yourself.
I'm David Black from the Open Software Foundation Research Institute in Cambridge, working with mock technology, looking at potential scripts and finding out what this looks like, what possibilities are.
My name is Carl Stork. I work for Palmeritz on OEM marketing for NT.
I'm Ellis Kelly from the Open Software Foundation. I work on user interface architecture.
I'm Simon Patience from the Open Software Foundation, the research institute in Grenoble, France. Also working with the server technology on the microphone.
I'm Randy Heap, Digital Equipment Corporation and Workstations Group, Palo Alto.
Doug Steeves from IBM and Austin, Workstations Division.
I'm Don Galbraith. I'm in charge of workstations for digital. We do all the mixed products, including the servers, and we also do the VAX workstations.
Chris Kernel from Digital Equipment, and I'm working in the Workstations.
Alex Bronstein, Digital Equipment, working with Chris Kernel and Substation.
Just before we get started, Dave is basically going to give you an overview of the system. The major focus for today is to really focus on what we call the executive, which is basically everything in privilege mode. We will touch on some of the work we're doing on non-privileged subsystems, both the Windows subsystem, graphic subsystem, etc. But the intent of the major presentation is to focus on things in the foundation layer, basically the kernel or the executive that runs in privilege mode. If you have questions on the subsystems, we'll have a couple of guys coming in later today talk about our Windows 32-bit subsystem, which is a subsystem designed to run Windows application with being stretched to 32 bits. We plan 2 other subsystems, basically an OS2 subsystem, which is actually fairly closely linked with the Windows 32 subsystem, and a POSIX subsystem. We'll be presenting the Windows 32 subsystem mainly as an example of what a subsystem does and looks like in this architecture. But we're not going to go through the subsystems in detail. So if you have questions on those, just dam them up and we'll probably arrange for a subsequent meeting. I know we have a meeting tomorrow with you guys to talk about subsystems, but if you have more questions, we'll probably defer those to pick them up later. The intent of the main presentation today is to focus on the foundation.
We're going to swap this out. Seems that doesn't work very well.
Big call going to come up through the other door.
Feel free to interrupt me at any time. And
can we get copies of those?
I guess we can.
I'll get contact Kelly.
Kelly's not here, but you can get copies of these.
I think they're there they are over there.
They're just, it's a 2-volume set and basically describes all of what we call NT, which is the privilege mode execution. It also describes
all of the Win32 stuff. It has some chapters in it also on OS2 on posits support. Okay, let me start out by kind of set the framework on the goals that we had for NT when we started this. We've actually been at this probably, well, about 2.5 years now, about the time I've been here. Portability is one of our major goals, and I think Paul said something earlier as I walked in about our goal for portability is to be able to port to a, quote, reasonable architecture in about 6 person months. And porting to an architecture means porting to the privileged architecture of the machine, not necessarily porting to whatever the system implementation is. If the system itself, in the way that we're building it, is completely divorced from the I/O model of whatever the particular platform you're running on. So writing device drivers and something like that is outside the 6 person months. A reasonable architecture is a page virtual memory architecture, similar to a 386, 486, MIPS machine, 88K. Unreasonable architecture might be, like a Cray, might be pretty hard to do because there's no virtual memory. When we say it's hard to do, it's hard to do compatibly. I mean, we're trying to build a system where we have source level portability without change, and porting to one of those architectures might be a little bit difficult. Actually, Cray would cause us a lot of problems too because of 64-bit addressing and so forth.
To be fair, the 6 person months doesn't include any development tools work, right? That's assuming you have a decent development.
Right. This assumes you have all the tools. Our experience so far has been that 6 person months is adequate time, ample time to do that. We've actually ported this and have it running on 3 different architectures. And the first one took a while to do because we had to split the source tree. But the second one we went to, which was the DEC Station 5000, we actually did that in about, I would say, about 2 months, 2 person months. So, anyway, we believe it's portable. We're developing it simultaneously for 2 architectures right now, which is the 386, 486, and the DEC Station 5000. We're doing that so that we can make sure that we maintain portability, we maintain the interface split that we need, and we don't go down a route where we put machine-specific code into the system where it shouldn't be. We can build the system today either way, and the build environment supports that. The second goal, a very important goal for us, is security. And we want to make sure that we built a system that had very pervasive treatment of security and inherent multi-user support. There's no security at all in the PC world today, save for what you get through logging on over a network, and that isn't really a log-on kind of thing. It's you identify yourself to the network server, and he then allows you to do things based upon that, but there's no workstation security. So we want to build a system that has workstation security optionally. You may want to run in a PC environment where you don't run locally with any security, but certainly the security has to be in the system because we want to use the same operating system for servers. And we want it to be able to support a multi-user system. We're going to certify the system at C2 because we'd like to get it certified within our lifetimes. And we believe that it's certifiable. It will be certifiable B1 with a small amount of work. Certification at B2 would require us to write a fair amount of design documentation that we just have not written and don't want to spend the effort doing right now.
The government process requires a lot of stuff.
Right. B2 is pretty expensive in terms of the documentation that you have to produce.
But I think it's fair to say that based upon your experience, you try to think through make sure we don't do
Right.
stuff that would give us a headache technically if we try to go for V2.
We sort of subconsciously try to think about things like storage channels and some of the other covert channels and make sure we don't put those in the system, but we aren't doing any rigorous analysis of the system to make sure that they aren't really there. We want to support multiprocessing. Our model of the world is symmetric multiprocessing. We believe that that's the form of multiprocessing we can best support. Asymmetric multiprocessing is not very interesting to us because asymmetric systems tend to be one-off systems. They're not very general, and we're in the business of producing software that we want to run across a wide range of platforms that can be specified architecturally, and software will run on them. That doesn't mean that it will not run on an asymmetric system. We actually have the system running today on the System Pro 2 processor system, which is asymmetric, but it is a shared memory symmetric system. The things that are asymmetric are interrupts and devices. The system supports, do you have a question? The system supports multi-threading at the system level. It's not something that's added with a runtime package, and we hope, well, we will be able to get enhanced single stream performance through decomposing compilers when and if they emerge on our system, and also just through multi-threading on multiprocessors where you're doing something that's actually split across multiple threads of execution.
We're trying to write all of our subsystems and extensions with this model in mind. So, for instance, our network code and transport code is all written to be multi-threaded. So automatically when we put that on a multiprocessor system, we should see an increase in performance there.
The entire system is multi-threaded. The file systems are multi-threaded. Basically everything that we provide is multi-threaded. Compatibility is a very strong concern of ours. We have MS-DOS. We have a system called Win3, which is a 16-bit Windows system. We're now extending that to what we call Win32, which you're going to hear a lot about later on today. We have OS2 2.0, which is a 32-bit system, and we want to be able to provide a high level of compatibility with those systems, and in some cases that means running the binaries. On a x86 machine, our goal is to be able to run OS2 2.0 binaries without change, and also be able to run Win32 programs without change. When you go across to another architecture, the goal is to be able to recompile and run those things without change. Compatibility extends beyond just the programming interface to the tools you use, the windowing interface you see, the file system on disk structures, the protocols we use on the network, executable file format, and a number of other things. One of the things that we see that we have to do to compete everywhere is to be POSIX compliant. This is a government requirement, and one of the goals is also to support POSIX compliant, which you could view as a level of compatibility with the POSIX community. The last major goal is extensibility. Our major goal is to be able to extend the system without requiring privileged execution and provide all of the architecture and framework to do that. We'd like not to have to dump a bunch of code into the most privileged mode of the machine every time we want to extend the system.
I think just to complement what Dave was saying is that those are all noble goals. The trick to do that is to do it without sacrificing performance or security. And I think a lot of what makes this system different, apart from clean, decent internal architecture, is a lot of thought went into essentially being able to run all those classes of programs, Windows, OS2, and POSIX programs, in a certain sense natively and efficiently without having to artificially map semantics and layer things on top of each other.
I'm going to talk about subsystems and in how we do these different environments. A little farther on here. Just sort of an overview of the NT architecture. We call NT a kernel-based system. And what we mean by a kernel-based system is there is a small kernel that sits at the bottom of the software structure close to the hardware that executes in the most privileged mode and does MP synchronization. It's the piece that has the machine-dependent things that are architecturally machine-dependent in it. Does thread dispatching, and it exports some things we call kernel objects, which are basically things that deal with either controlling the environment of the system, or they have to do with dispatching threads. Kernel objects are, I'll give you a few. Threads are kernel objects, processes are kernel objects. There's also a number of synchronization abstractions that are kernel objects. But there's also some things that don't have directly to do with machine dispatching. They're there too. Well, it does interrupt dispatching. It's the piece that does the interrupt dispatching to code. The executive sets on top of the kernel, and it runs in the most privileged mode also. And I guess the big difference between the kernel is the kernel is the slowest layer, and it's non-preemptible in the sense that we don't context switch it, but it's preemptible in the sense that we can interrupt it and execute interrupt service routines. The executive sets on top of that, it's totally preemptible. It's multi-threaded. It provides all the I/O capabilities, virtual memory, process control, synchronization, and something we call LPC. These are all the abstractions that are exported to user mode. The executive, in some cases, takes the kernel mode abstractions and wraps a wrapper around them to provide user mode access, whereby you can name and protect these objects so that just anybody can't access them. Which leads to the next point. The system is object-based in the sense that the executive exports to user mode a set of objects. Everything is accessed in a uniform, pervasive manner. Objects are addressed by handles. Handles are private to a process. The functions of dupe and all that sort of thing can occur between processes. You actually can dupe a handle between processes. And the big thing about the object-based stuff is there's one place in the system where you translate a handle to a pointer, and that's the place where all of the access protection checks take place. There's pervasive naming of objects so that objects are named in the same way all objects have the same name structure, and there's pervasive sharing semantics for objects. All objects have an ACL on them. They can or cannot have a name, depending if you want one. The system is extensible. We talked a little bit about extensibility. We can extend the system in 4 different ways. Loadable device drivers you can think of as being a way to extend the system. Device drivers aren't built into our system. They're loaded dynamically when you boot the system, or they can be loaded under an operator or somebody that has the privilege to load a driver. That does take a privilege if you're running in a secure environment. You can't just load a piece of code into the system. Obviously, you want to load something that you think is a good piece of code into the system. We have an installable file system structure. You can write file systems and install them into the system dynamically. Protected subsystems is the way that we supply the multiple operating system environments. And the last way is kernel extensions, where we actually will allow you to load code that extends the kernel and provides new services dynamically. So there's 4 different ways we can extend the system. Our preference to extend the systems with protected subsystems. Installable file systems are sort of the thing. If you want to have a particular kind of file system, then you might want to do file system. Device drivers are sort of a must thing that you have to do to support some system platform.
They protected subsystems.
They run in a separate address space. They have ways in which they can impersonate clients. They can have the protected subsystems are started when we start the system, so they can have enhanced privileges if you want them to. There's nothing to say that anybody can't write a protected subsystem and have all those things, and it's protected from its clients in a sense. When I get on some of the things like the process structure, you'll see that you can write a protected subsystem that can completely control its clients and make sure its clients can't do anything that would cause it not to have control. The network support in NT is integrated into the system. We support two pieces of network that's compatible with our own Landman product, but we provide a general transport interface for any transport, and we're perfectly capable of supporting what we call multiple network servers and redirectors. A redirector is just a remote file system. It's the client side of the remote file system.
I think, just if I can make a comment there, the point is here is we are actually, as part of this effort, implementing a LAN manager client and server. However, the general architecture that we provide to support networking code is not specific to LAN manager. The LAN manager client software just looks like another installable file system in particular. And the server software, one of the things we learned trying to make OS2 a decent server operating system is that the traditional architecture of basically making the server a user-level process never gets you to be performance competitive. And we've tried to rethink what it really takes to make a standard operating system a high-performance network server. And the primitives that we've built into the system, common cache manager, etc., are available as standard services of the system. So you could actually take these services and implement a very high-performance NFS server or a very high-performance Novell-compatible server if you wanted to. And the general architecture primitives are general and available to any extension in the system.
That doesn't mean, however, that you couldn't do an NFS server too as being totally processed or user mode process based.
The issue is what trade-off you want to make between where you're extending the performance you want.
Sort of a system block diagram of the privilege mode of execution. We only use two modes of execution no matter how many modes in the real machine. The least privileged mode we call user mode. The most privileged mode we call kernel mode. Applications and subsystems run in user mode, and the executive and kernel, device drivers and so forth run in kernel mode. I guess that's kernel mode for the first time, not user mode. At the bottom of the picture here we have the kernel. I talked a little bit about the kernel before as being the piece that does the MP synchronization. It provides thread dispatching, and it exports the kernel objects. It sets next to the hardware. You can imagine the hardware is being down here, and it deals mainly with the privileged architecture of the host system. It exports to the executive, which we've talked about this being more or less the executive. The device drivers are sort of part of the executive. It exports this set of kernel objects, and there's about a dozen kernel objects. They're all in the notebook there. So the other layer that we have here that's set sort of next to the hardware is device drivers. I just threw a few in here. These are kind of the standard PC devices you see. A Mac driver is a network driver that conforms to an interface we call NDIS, which is sort of a operating system independent interface that's been developed between Novell and 3Com and Microsoft and some other people, whereby a hardware network vendor, an IHV, can produce a Mac driver that conforms to this particular spec and put it in any one of these operating systems by doing the appropriate assembly or whatever to build a device driver. Transports are transports. Other things that might be up here are, things you might see in other systems. You might see tape. Basically, any kind of driver you want to add. Sitting on top of these two pieces is what we call the I/O system. The I/O system is the application interface to the I/O system. You can think of this as being open, close. Yes?
You said the device drivers are essentially part of the executive? So they're almost executive part of the executive?
Well, yeah. They're sort of,
Does that mean they're preemptible and all that stuff?
Oh, yeah. I mean, the parts of them that are preemptible are really preemptible. Parts of drivers, though, run at interrupt level. That's only preemptible by higher level interrupts. We also let drivers, there's a mechanism in the system called deferred procedure call, which lets a driver defer work to a lower priority level after it's done whatever it has to do to service the real-time requirements of the device. And during the time they're running at this level, deferred procedure call level, effectively we're non-context switchable. Right?
Basically, the device, to say, Dave, is really just two pieces of code, which is the kernel and the interrupt level processing parts of the device drivers that really run as non-interruptible, non-preemptible, high priority code. Everything else just becomes processes that get scheduled.
Well, there are some pieces to the executive where we use spin lock synchronization for small sequences, which are during the spin lock sequence.
But in general, it's true that the rest of the executive, let alone
it's all preemptible.
let alone the applications and subsystems, will get full benefit of having a so you put multiple processes in there, not just your application, but your executive is going to go faster.
So your DVCs are preemptible and schedulable?
No.
So the interrupt part...
They're preemptible, they can be interrupted, but they can't be context switched. Right?
That making a
But
difference?
in an empty system, you can have multiple of them executing simultaneously.
Trying to make a difference between preemptible, which is kernel decided, and interruptible, which is hardware decided. Trying to see where the pieces fit.
Right. Well, there's a piece of a driver that can run non-preemptible. Right. Device drivers, by the way, are written totally in higher level language. Our implementation language of choice here is C, but the total driver is written in C. The interrupt service routine, everything is written in C. The device drivers know about the system structure with respect to whatever host they're running on. So they understand something about how the I/O devices are connected to the system. We provide a fairly large library, I guess what you'd say, of routines to help you make the abstraction to whatever the hardware is. And the intent of NT is that there will be loadable code that behind those interfaces that's supplied by a host vendor that implements those abstractions on a particular system. So you would see a different implementation of those on, for instance, an x86 than you would on a MIPS system, and then even on a MIPS system, depending on who built it, you might see a different implementation based upon whatever I/O buses structure they're using.
But I think the other point I think Dave will come into later is that the I/O subsystem, the device drivers, essentially form a layered hierarchy of routines. And we have the general concept, like streams, of a layered architecture.
Yeah, actually, I missed
You layer
that.
things on top of each other, and basically, you go to a new device, you're typically changing very little code. A new disk driver for us is literally man-hours or man-days of work to get a new disk driver out. Depending who's doing it.
Actually, I missed the last point on the previous slide about the I/O system. The I/O system is completely layered. And what that means is the device driver model is completely layered. And you can build device drivers on device drivers on device drivers on device drivers. So if you want to build abstractions that way, you can do it. It turns out that the SCSI is a nice example of building abstractions that way, where you build one driver that deals with whatever the SCSI protocol hardware is, and then you build a driver that sits on top of that for tape and for disk and for CD-ROM and whatever else you might want to have. File systems are sort of like device drivers, except they have a few more internal support routines that they can use. We actually have 3 file systems that we support. One's called the redirector, is the landman redirector. These are a couple file system structures that we support. FAT is the traditional floppy format structure. HPFS is something that we get put out, I guess, about a year ago, which
It's an OS2 file system.
is an OS2 file system. The I/O system itself
We actually
provides.
also have another one, which is a CD-ROM ICO.
Yeah, we have a CD-ROM file system to this pictures. The I/O system here is the piece that exports. You see the NT APIs. It exports the interface to all of these things. And basically, you do an open, you get a handle back. When you do an open, you ask for some desired access rights. You do the open, you get a handle back, and that handle now, if those access rights can be granted, it grants you those access rights. The access rights are stored with a handle, and now every time that you access that particular, whatever the object is, whether it's the device directly or through the file system, your implied access by the function that you're performing will be checked against your granted access, and of course, if it can't be granted, it's rejected. We don't go through any ACL scan every time you access an object. The object manager is the piece of code that does all of this stuff with access checking. It translates the handles. The object manager also has some APIs that it actually, some NT APIs that exports, but in general, the I/O system calls pieces of the object manager. Memory management does. This interprocess communication piece does. The process structure does. There's some routines in here that do the translation from handles to pointers and does the access checking.
Like one more comment as well. Each of those are formalized interfaces. In other words, there are formalized interfaces between all the pieces of the system. So in your notebooks, you'll find all basically the entry points and service routines that you use to get access to object management, executive support routines, etc. So even though all of this is running essentially in one privilege mode, it is a completely formally layered system in terms of well-defined hardened interfaces between each of those components.
That's something that I don't really talk about, I guess. Probably should, is that we sort of designed, I mean, I've drawn these as boxes, and we really designed these like boxes. And we tried very hard in the system not to have anybody reaching behind the back of anybody else, so that we have dependencies in the code that would prevent us from replacing the implementation of a particular box. There's more boxes than we actually have shown here, but each one actually has a formal interface, and in general you communicate with that through pointers to opaque objects. Memory management supports virtual memory. It supports map files. It supports demand paging. It also knows a little bit about the hardware. We decided that we would make the split memory management so that it has much more knowledge about the hardware than, say, Mach does, where there's this really big split between what the architecture is and what's happening. And the reason we did that is to get the most efficient paging that we could get in a system that we thought was going to be our major market to support, and that's a 386, 486. It turns out that most of the RISC machines support that same kind of page architecture, so there's not a great deal of problem in doing that. We would have a little bit of difficulty, I think, supporting VAX memory management because of the way the page tables are separated with a physically contiguous system page table, but that would be a very drastic thing to do. If you wanted to support something like Cray 1, then that's probably the major piece where we would see there would be changes in the code. Interprocess communication is something we call LPC, which stands for Local Procedure Call. It's the mechanism that we use to communicate with subsystems, local subsystems and not remote subsystems. It's very high speed. It gives you several different ways in which you can communicate with a protected subsystem, and the subsystem can communicate with the client. At the fastest level, if the number of parameters that you're passing through are small enough, they just get passed directly through the executive. Moving up one level, the client and server can actually double map memory so that the client and server share a window that is unique to that client-server pair, and the client therefore can see nobody else's window besides its own. The server, of course, sees everybody's window, but all mapped in different places in the server's address space. That can be used as a higher speed mechanism to shuffle information back and forth. You can also, in the server, if you will, or want to, you can double map the user's address space or the client's address space directly into yours, which is a little different than saying we have this window. That means that you can map anything dynamically you want to. And the last one is that the server can actually read and write the virtual memory of the client without mapping it. So that's sort of moving down the scale from fastest to slowest. The primitives that are provided for LPC provide all of the kind of interchanges that you want to make, where the server basically says, sitting there and says, I will accept the connection through my port, and when it accepts the connection, then it has all of the exchange things to do. It says things like reply and wait for another request, so that we don't end up with several system calls in and out of the system to do those things. I mean, there's like combined operations.
And I'd like to comment there as well, Dave. Clearly, this is one of the questions that always comes up is does this process communication work locally and remotely? Our view is that you could layer, you can, and we will layer on top of this a general RPC mechanism that will then work for either local communication or remote communication. However, the reason we didn't just say there's one and it works, locally or remotely is we found that by doing statistical studies, particularly for, say, in a graphics environment, we have a client calling into a graphics engine. It's not uncommon for a client to be doing 2,000 plus calls a second into the subsystem. And you've got to really, really get very high performance context switching basically between the client and the server. So complementing these very high performance local optimizations, we will have a general RPC mechanism which is being developed in conjunction with OSF, is compatible with OSF both at the syntax and at the wire protocol level, which is being developed and at this time will be available in this environment. So it's really a programmer's decision. Do you want to write your client subsystem in such a way that it will be general and work locally and remotely, or do you want to restrict yourself to the local environment that would get literally a transition time between client and server measured in microseconds as opposed to milliseconds?
My understanding, you say that this is this LPC is between clients and kernel subsystems, or it's clients and other client subsystems?
It's between clients and anybody.
Any other client on the same processor?
Well, the same processor complex. Right. In fact, we use LPC ports to do upcalls effectively in the kernel also, where we get some event in the middle of the privilege mode of execution, and we want to make something happen in user mode. We generally use LPC ports to do that, and I'll give you some examples later on where we use that. The debugger is one of them. The process structure is very simple, very straightforward within the system. Actually, later on, I'm going to talk a little bit more about the process structure, but we're trying to build a system here that we can sort of model anybody's process structure. So what this one exports is processes and threads, and processes and threads have access control on them. And we have enough access control so a subsystem that's emulating an operating system can create processes and threads in such a way that the clients can't really do much with them except call the subsystem to get some kind of a structuring, to get things like signals done, or all the things you have in Unix job controller, some of those things. So that there's no structure at all imposed by NT other than a set of threads runs in a process. And a process, when you create it, can have a parent template. But as soon as the template is used, it's gone. We actually implement fork directly here. Fork is done almost exclusively as copy on write. We don't copy anything on fork. So when you start up in the forky, and you try to reference memory, then you probably get a write and protect violation, and at that time we'll copy it. The security authority is, this is another piece, or one of the pieces of the security authority. There's another piece that runs in user mode. This is the piece that's referred to by the government as the reference monitor. This is where you put all in one package, all the stuff that does access validation with ACLs. It does alarm logging, it does audit logging, and all of the things that you're supposed to do for a secure system are done in one single place. We don't spread any of the access checking around in the system. You call formally specified routines there to get access checking done.
One of the nice things about this system, which reflects again our experience of trying to build real-life client-server systems, is that Dave will explain later on, even when you're running a LAN server, the access checking is still occurring down there. One of the things you probably know when you try and implement servers in a LAN environment, if you're not careful, you find out the server's having to do access checking on behalf of its clients. And using some facilities that Dave will describe later on, we can, even in the distributed environment, isolate all security checking down.
Actually, I've almost skipped over the server here. This is our LANman file server, and it runs in kernel mode, but it really has a separate process and a separate own set of threads. And basically what it gets is it gets a request that was generated by a redirector on a client system to open a file. And when it gets that request, first of all, the client has to be known to the server. That means it has to be logged on to the server. Log on can occur in several ways. One is the client explicitly logged on the system running the server, or the client is running in the domain where the whole domain knows what the security profile is of everybody, so the server can locally find out what the profile of the client is. But what the server then does is the server impersonates the client and then just calls standard NT services to get its request done. And that automatically enforces the protection checking and access control that would have occurred if the client itself had done the access. So this server doesn't have to have anything that deals with, oh geez, I wonder if my client can do that. It does not deal with that. What he does is when one of his threads does a request on behalf of the user, he sets the security profile of that thread and does the operation using a standard NT interface. Now, one of the things that sort of implies is NT is a recursive system. All of the code in here can recursively call these APIs. All right, so a file system running in here can call NT open if it wanted to open something, or if it wanted to go out of the network, it could do that. If it wanted to create threads, it could call an NT service to do that. So basically all of the NT services are available to everything that's running in here. The kernel, of course, doesn't do, the kernel makes no calls in this direction at all. The kernel is sort of a passive thing that you call, and he does whatever you want him to do, and eventually, hopefully, returns.
Those are general services. So we, as I said earlier, we have a landman server there, but you can create other processes that run in privilege mode and can use all those services. So you can do other protocol servers, other extensions, whatever it is that you wanted to extend the system with. And it has a complete set of APIs that are available when they're generalized.
One thing nice about running a process in kernel mode like this is the fact that it still has a user address space. Although none of its threads ever run in user mode, it still has a user address space. So it can do things like caching if it wants to in a fairly large address space, whereas the system address space is constrained and there's a finite amount of it. I didn't mention before, but drivers can be thread-based if you want them to be. In general, our drivers are not thread-based because they execute initially in the context of the client, where the client is either somebody that came all the way in from user mode. We call this BYOT. It's called bring your own thread. And we can use the client's thread coming in. It might be a thread that's running in the file system. So when you initiate a request, which means I generated this request, and I'm all the way to the driver, and the driver's going through its code to say, geez, you know, is this legal, and so forth, and whatever. The driver then generally queues that to its routine, which is called its start IO routine. If the device is busy, then the queuing operation just queues it and returns. Otherwise, what happens is you bring your own thread and you continue right into the start IO code, which then does whatever synchronization it has to do with the interrupt service routine that could possibly be running on another processor, and it starts the device. The thing that happens after that is some later time you get an interrupt, and the interrupt captures whatever the real-time information is, defers the rest of the processing to what we call this DPC level, and then just dismisses the interrupt. The DPC then runs, and the DPC then decides what it's going to do, and generally what it does is it signals some kind of a synchronization object that wakes somebody back up to do something with that request. We do page unlocking and that sort of thing though at the DPC level, so we really don't have to go all the way back into somebody's thread to unlock pages from memory.
Regarding your NT recursive statement, is that true also in the kernel? And the kernel wanted to log some sort of error in the log file, the kernel would just do an NT open file?
I think I said something about the kernel doesn't call this way. This piece does not do that. If the kernel wants to do something like that, and I'll give you an example where the kernel does want to do something like that, and that is, there might be some kind of a hardware error, like a memory error, where we want to log some information about a memory error. We want this code logically to be part of the kernel because that's the part that looks at the hardware. But on the other hand, it has no access to any of these things. So generally what it does is it puts the information somewhere in a prearranged place that we've conveniently architected that way, signals some event that says, hey, there's some information here, and then there's some daemon thread that's running in kernel mode that empties that information out, probably dumps it into, well, it could be a thread that dumps it into an LPC port that somebody gets, or it could be something else like that. This is recursive, but there's a finite level recursion. Right? The finite level recursion is the size of the kernel stack, and kernel stacks are restrained in size because they have to be resident in memory.
You already have some out-of-stack errors in the executive.
Pardon?
It's like on the list machine, you have an out-of-stack errors on your executive. You have the wrong code.
That's right. In fact, if you run out of stack, you stop real fast.
Could you say the specific reasons for why the file server is in the kernel as opposed to
the file server is in the kernel because the experience that we've had trying to compete with network file servers, mainly Novell, dictates that to get the performance that's required, we have to have it running where it can have direct access to a common cache manager that's shared by these Mac drivers, transports, and the file server.
I can give you just a few words on that. we initially implemented our LAN manager server on OS2 in the traditional architecture, basically of user level process running. And as soon as you've got, what you find, as soon as you've got a decent disk cache, so you're no longer constrained by the disk performance, the next thing that happens is basically the CPU itself just becomes pegged. And what you find you're doing is essentially two things. One is copying data between levels of abstraction. So you're copying data out of the buffers of the low-level driver to the next level of driver, up to the server, down the file system back. So you're just doing this constant block moves of information. And secondly, you're doing context switches. And if you want to get a system, which you need to do to be performance, is to be able to sustain 800 or a megabyte per second, 800K bytes or a megabyte per second of sustained throughput on the LAN, which is what you need to really be competitive, then you've got to solve this problem in an architecture, in a way, solve the problem of redundant copies of data, and solve the problem of context switches. We have a hack in our...
Can you solve the copy problem just by mapping the memory into the user process?
Well, you have to, there's several layers here. You know, you have basically like an Ethernet driver, and you have a transport, then you have a file system, then you have a server, right? And it's very difficult to map that all the way down and all the way back up without actually having to transition. Well, it's hard to do the mapping. And then if you put it out in user mode, then you can't execute it without really doing a context switch or an address-based swap, which is equivalent to a context switch. There's no reason that server could run totally, well, a server, this particular one couldn't run that way because it calls our cache manager directly. But you could write a server that did not do that. It absolutely did not do that. And it would run according to
basically the way we solve the problem is to have a common cache manager that's available to device drivers, file systems, and the LAN server. So when the request comes in off the Ethernet card, we take that 512 bytes of data that comes in with that packet, we put it once in the memory that never moves thereafter. Thereafter, people are just passing pointers to it, essentially. And the other is to put the server process in kernel mode so we're not context switching.
There's more than one way to skin the cat, and we're willing to spend the time to put this in privileged mode to make it run as fast as we can make it run.
I mean, the file server is in kernel mode, so you sorry, it's a separate process, so you are context switching, you're just not address based.
No. We only context switch for certain things. To open a file, we context switch. But to do a read or write, we will not context switch because the system part of the address space is mapped into every process, and it's common. And therefore, we do not have to do a context switch. It's all procedure-based at that level. All of the way in which it deals with a lot of the things here are all indication-based, where what you pass down is you pass down the address of a callback procedure, and you get called back on indications on things. So we do not do the context switching in almost all cases.
Basically, what you see here in general is an attempt to build a layered subsystem in the same way that Mark is layered in a nicely way. We have strong abstractions between each level. At the same time, to get the performance that we're going to need to be able to compete with systems like network, etc., in a real commercial environment, and to do so in a pragmatic way so we can get the performance but not compromise the structure of the system. And you have to make some compromises, but we're trying to make these in an architected way as opposed to hacking pieces of code into the system, which is what you find happens if you don't do that. Is people take Mark and they hack it in order to try and get the performance that they need. And the next thing, you've lost extensibility, you've lost security, you've lost structure, etc.
Your decision to put the file server on top of the NT API as opposed to inside the IO system box simply because you wanted the file server not to worry about access control techniques?
That's one of the reasons. That's a major reason. I mean, to really draw this right, you know, there's sort of some of this, right?
Because since you said that the little boxes inside the IO subsystem are allowed to call NT APIs, there's not a big difference between sitting in, except for that access control.
The file server uses these APIs mainly for the access control purposes, right?
Right.
All right. It also uses some of the internal APIs directly also.
But you said that the box inside the I/O subsystem would be allowed to call something in the NT API.
Right.
So,
You could have put it down there, is the
so
answer.
then that.
Well, it would be
then that
difficult to put it there because the file server is dealing with the transport in this direction. Right, I don't know how, what do you want to put, why do you want to put it here? It's really something that sets outside of this, and it uses some of these services. It won't run any faster if you made it you want to make it an installable file system, or?
No, I don't want to make it different. I'm trying to understand why you put it out. The first reason you gave is that it needed to call the NT API so that it wouldn't have to worry itself about its self-control.
That's one of the reasons, right?
Yeah, that's perfectly reasonable.
Right.
And then later you said a box inside the executive could also call the API and therefore have the access control done for free.
Right,
So
but
then
there's
I
no,
felt-
see, if you put it,
So then I didn't understand the reason for having it sit out anymore.
because there's nowhere, it doesn't belong in here. I mean, it would just be an island, right? We could draw a box down here, but there would be nothing that connected to it. The only connection to that server is this direction, right?
It's really, he's drawing it that way to show you the abstract structure of the system.
Right.
This
I
is
mean, I
basically levels
I
of
could draw the
abstraction.
box in here anywhere, but there's no route through these boxes to get there other than like this.
That's fine. That's what I hadn't seen before. Because the first reason you gave was so that it would call the API, but then you said that someone inside could also do it, so I found why that was so.
Could make this island on the inside. Okay, moving right along. In the copy you get, there's one more slide that sort of verbalizes what I said about that picture, so. Right. Here's what the user mode side of the execution looks like. We have some pieces that are provided by the system. You can think of these as being daemon processes. We have the other part of the security piece, which is this guy mainly deals with authentication. We have somebody called the session manager. The session manager is kind of a traffic controller that controls traffic between server subsystems. Server subsystems being subsystems that provide operating system environments. And we have a daemon, which is called the logon process. There's a logon process for every type of device that you can log on to the system with. Notice I said type, and I didn't necessarily say every device. But think of the fact that in some systems you log on through a windowing interface. Some systems you log on are dumb terminals. Some systems may have smart cards you run through a card reader. Some systems could have fingerprint readers. Some systems could have voice recognition, right? Each one of those kind of types would have a logon process. In general, what we supply with an OS2 or Win32 kind of system is we provide a logon interface that works with a graphical user interface. And generally there's only one display, so he's only handling one particular display and log on to that particular device. These little connections here are LPC connections. LPC connections are guarded by an ACL. Also, in the case of server subsystems, servers launch clients, and so they know who their clients are. There's a 64-bit ID that describes a client, and therefore a server subsystem can make sure that it doesn't deal with anybody that isn't one of its clients. The security authority, basically logon collects authentication information, whatever's needed to authenticate the user. Passes that information to the session manager and says, I have somebody that wants to log on. We will need a session for this guy. The session manager talks to the security authority and says, I got a guy who wants to log on. Do you know about this guy? And the security authority piece could go out on the network to a name server. It could go out to what we call a LAN-man, a domain controller, or it might have that information locally. It's the piece of code that generates what we call a token. A token is an object that holds the access rights of a subject. That's generated and effectively placed in the system, and then the session manager uses the session manager's process, puts that information in the system that will be used by the other security authority piece. It contains all your access rights in terms of what groups you belong to, what environmental access rights you might have, like for instance, whether you're local, remote, or things like that. You came in over the network, because quite often you want to distinguish between access to objects by people running locally as opposed to access to objects from people coming in over the network. It contains whatever groups you belong to, and then there's a bunch of things on these rights that allow you to either optionally use them or not use them in your current active profile.
What's the difference between what you call a token and what OS people usually call a capability?
A capability is really something that's given to somebody that gives them the right to access an object. And a token what we're talking about token here is all your identifiers and privileges that describe what rights you as a subject have. All right, somebody might use, if this was a capability-based system, somebody would use that profile, that token, to generate a capability for you to access some particular object. Typically, the system consists of one or more operating system environment subsystems, and these are subsystems that this is what I call Win232 server and the OS2 server. There's actually another one that we have that implements POSIX. These server subsystems run as protected subsystems. They launch their clients. They communicate. I don't have a line here, but they do communicate with the session manager. They're capable of launching programs across each other. They do that via the session manager. They actually have a connection to the session manager through an LPC port. These ports here are protected in the sense that these people are the only people that can talk to them. The session manager also has a port to these guys, and he knows who they are. It's established when we boot the system. I suppose we could establish it later on by anybody that said, I want to start up another subsystem. Subsystems deal with their clients through LPC. They have a well-known LPC port. They can decide whether or not they want to discriminate among their clients. Generally, they do. For instance, you don't want Win32 and OS2 to get their process structure mixed up. So in general, you don't want programs that are OS2 programs executing operating system calls to their server subsystems that are Win32 calls, and vice versa. And the same thing with POSIX, because it would get even more messed up. Client processes call the subsystem through LPC, and they also can call NT directly. So to get a little more detail about what the subsystem components look like, one thing I ought to stop and say something about is what is a DLL? A DLL is a dynamic link library. The whole structure of NT is very dependent on dynamic link libraries. And these are basically shared libraries that have a part that's shared across all clients, and they can have own data that's just copy on write data, or you might think of that as instance data. They are dynamically mapped into a process when the process starts running. We actually snap all of the links for all of the DLLs that were defined at the time that the client was linked. This is the client application. The client application, however, can also load further code as DLLs and get those links snapped dynamically through some calls that allow it to find entry points in the loaded DLL. Okay, so we talked a little bit about the Win32 well, this is Win32 about the server process. The server process in general implements all of the things about the operating system environment that require global state. Right, and a good example of that is the relationship among processes, whatever kind of a process structure you want to have, and which threads belong to which processes. If it has some kind of messaging system or whatever, then the messaging storage might be there. But in general, it holds the global state across all of its clients running in the same kind of environment. Not necessarily with the same security profile, but the same kind of clients. Over on the other side, the server communicates with NT interface, and it also communicates with the client through LPC. On the client side, we have the client application, and then we have an interface that you can think of like an RPC, set of RPC stubs that actually interface to the server subsystem. Now, in general, what we try to do over here is anything that we can translate directly to an NT service, we do. In fact, almost all of these let us translate I/O directly to the NT service, because the security model and the file system capabilities we have let us emulate all of these environments we have today. If we were to try to do a little more richer environment, then we'd probably have to create another file system to do that. Or we might decide to put some of the semantics over here. I don't know. It depends on how often you want to make that traversal. But in general, we try to do as much over here in the client DLL as we can. Like I said, this is a set of stubs, and the stubs may be large or very small. If they're very small, generally they'll go through the LPC mechanism. If they're a little larger, they may cache information. For instance, these guys typically like to have their own idea about how you refer to one of their objects. Like they have their own handle space. It has nothing to do with the NT handle space whatsoever, but they like to hand out handles. And generally some of these are small numbers, some of them are big numbers.
It can also be handles to Windows, for instance.
Or it could be handles to Windows. In general, what we do is we try to cache that information. If it's a translation from an NT handle to an environment handle to an NT handle, we cache that information over here. So the whole idea in building one of these things is to try to get as much code over here as you can and make this traversal as infrequent as you possibly can.
The requirement for traversal is if you need access to global state.
If you need
access to the window or whatever global state, Win32 global state, then you know you have to traverse.
Well, in general, you don't get access directly to any global state. All right.
I think of what you're calling needs to affect.
If a function that you're going to invoke needs to affect global state, you make that traversal.
Like create thread, for instance.
Actually, it turns out Win32. Yeah, Win32 does make that traversal and create thread.
The other point is Dave showed a line directly from the client application down in kernel mode. That's really a theoretical statement that the application could, if it wanted to, call the kernel directly. We will not document the kernel interfaces generally. We'll make them available to subsystem writers. But we're not trying to define new operating system interfaces. What we'll document our programming documentation for general ISVs is either the POSIX interfaces, the OS2 interfaces, or the Windows interfaces. So in general, every time an application program wants to get a system service, it calls the client DLL, which then basically makes a decision as to how to handle that service, either by passing it on to the kernel or by kicking it across to the subsystem, or by virtue of caching, doing the work itself.
Do you ever send broadcasts from the server process out to Summerall, the client DLLs, to update and swing the state?
No.
You don't need to.
You don't need that.
Because there's no caching of information in the
The only information
There is
that's cached. The only information that's cached, though, is only
local
with respect to that one
that
particular process.
That can't change in global
Right.
state without that process.
We never do any of the thing you're talking about.
In theory, you could, though. The primitives are there to do it.
Yeah, I mean, in theory you can do that.
You said in principle, you're not going to advertise the NT interface, you expect less IPs using all interfaces.
It's not old, they are, the interfaces, nothing old or bad or anything about it.
Doesn't mean that people were worried about performance and database functions, but the first thing you're going to do is scrap all that and start calling it directly.
Our general feeling, we've actually spent a lot of time talking to the ISVs, Sybase, Oracle, etc. And I think they're actually very happy with what they're doing and with the interfaces, iOS 2, Win32 that we're exporting.
Actually, in general, a lot of those people have some kind of an abstract layer in their own software anyway, so that they can port from system to system. So they don't directly go after things usually at the operating system interface level anyway. They have, if you will, they write a set of stubs every time that they want to go from one environment to another one. Now, the rewrite of the stubs might be fairly small if they're going from Unix system to Unix system. But if they were going from Unix system to VMS system, or they were going from Unix system to one of the larger IBM systems, then the stub effort might be more.
We reserve the right to document that if we need to. But our feeling is right now that for most of the applications we looked at, we want to do that.
The place where you might want, I'll give you an example where you might want to do this, is if you were running, you had a program that was going to run in a particular operating system environment that didn't have some of the capabilities you really wanted to get a hold of, like asynchronous I/O or map files, then you might do that. All right. Some of these subsystems will provide that. Win32 does. It has asynchronous I/O and map files. Unix doesn't have asynchronous I/O, so that might be a case where you might say, geez, maybe what you would want to do is have an extension of the Unix. The best thing to do is probably have an extension of the POSIX interface that says, this is the way you do asynchronous I/O. If you implement asynchronous I/O, and oh, geez, by the way, this system does that.
Presumably a client who uses both types of subsystem calls and the NT curl mixes and matches at his own risk, because presumably he's using the NT interface, he's capable of reaching around the back. And
no, that's not true. He does not do that at his own risk. It is the subsystem's responsibility to make sure that he absolutely can't screw himself. All right? And we make sure he can't screw himself. We make sure that our subsystems are done in such a way that no matter what he executed as far as an NT service was concerned, if he was doing an operation that would affect the global state as held by the server, then there's an access control list on that object that's created by the server that he can't screw with. He can create NT objects and totally run within that environment, but this guy over here doesn't know anything about those. But any object he knows about, he makes sure that the client can't subvert him.
The way that you can fuck yourself if you do that is by basically delete that from the tape. The way that is that you sacrifice portability if you do that, because these are interfaces, API sets that are available in other environments. Windows 32 will be available on top of DOS. OS 2 is available on top of OS 2 2.0. POSIX is available on other Unix systems. So to the extent that you stray outside of those interfaces, what you're sacrificing is potential portability.
What's the token gets generated? Back to what's it associated with inside?
It's associated with a thread, right? Initially, what happens is there's a token associated with your process, and by default, that's the token that's associated with each one of your threads. However, when you receive a message over an LPC port, you can interpret or you can impersonate that particular client. And when you do that, the token of the client gets associated with your thread. And you have some capability to switch back and forth between your own security profile and the client's security profile. So it's really thread-based. It's not process-based, but the default comes from the process.
Can the client diminish the credentials in its token if it knows that that token will be passed to a subsystem that doesn't quite trust?
When there's control, when you pass a token you can say that there's like 3 levels of trust that you can give the subsystem. You can say, I don't trust you at all. You cannot impersonate me. And you might do that for something where the subsystem is providing some kind of a service. And you don't want him to go delete your files or anything like that, right? There's a case where you want to say, geez, I'm going to give you some rights to some of my stuff, but some of my other stuff you can't get rights to. And in that case, you have to have some rights that you can shut off. That's part of your token, so you shut those off. There's another level of it that says, I will delegate to you the ability to delegate to somebody else my credentials, so that you call the subsystem and say, you can impersonate me, but you can't call anybody you can't call anybody else and have them impersonate me. Right? So there's 3 levels.
They're not all mutually exclusive.
They're not all mutually exclusive.
What you're saying that the right, owning a right does not give you the right to delegate.
That's right. If you own the right, you can delegate it. But if you were given the right by a client, you don't necessarily have the right to delegate it.
And do you worry about revocation?
No. One of my favorite topics. Okay, now does anybody want to take a body break or anything? Take a body break. Okay. Because we're sort of going to go 48K of memory, and it's about 48K on both the 386 and the 486. It's not a great deal different. I'm sorry, on the MIPS. The MIPS code is a little bigger than the 386 code. It does thread dispatching, the multiprocessor synchronization, it does hardware exception and interrupt handling, and the low-level machine functions. We generally don't have any policy in the kernel. But there are some very subtle things about the policy, particularly the way that it does priority degradation of the priority of threads. It basically implements a preemptive priority scheduling system with 2 classes of priority. One class is called real-time priorities, and there's 16 of those. And one class is called variable priority, and there's 15 of those. Within the variable priority class, the system feels perfectly it feels perfectly at home at changing those priorities as it sees fit. Within the real-time class, it never changes the priorities. The real-time classes, round robin, however, is quantum in. So within a particular class, you round robin within that class as you hit quantum ends. Within the variable classes, you execute with a base priority, and as events occur, your base priority, as events occur, your priority is augmented from your base to a higher level, and as you execute at that level, you experience quantum ends, and your priority decays back down again. It turns out to be quite a efficient way to do it. But that's a piece of policy, more or less, that's built into the system. However, the executive has control over what it sets the base priorities to, so it can give favorable treatment to one process versus another. We talked about the pageability and the objects. I'm going to say a few words about exception handling. We implement per-thread, frame-based exception handling with the ability to catch all exceptions. We do not implement any signals at all in the system. If an environment implements signals, then that is the province of that environment subsystem, and indeed there is a way that the subsystem can suspend its client, get its context, change its context, include pushing things onto its stack or whatever, and then restore its context and resume its operation. So we indeed have signals in OS2, and we have signals in our POSIX subsystem, but the system itself does not implement signals. The mechanisms that are in the system are get and set context and read and write virtual memory and suspend and resume. We support software as well as hardware generated exceptions. Means you can raise an exception in software and it goes through the system in the same manner as it would if it was generated by the hardware for an access violation or whatever. When we go look for a handler, this is the sequence that we go through. The first thing we do is we say, was there a debug port associated with this thread's process when it was created? And this is an example of an up call. And if there was a debug process associated, a debug port, then we will send an exception message to that debug port and wait for a reply from the debugger to say whether or not it wants to handle that exception. If the debugger decides it doesn't want to handle the exception, or there's no debugger port, then the next thing we look for is a frame-based handler. And frame-based handlers are per procedure frame, and we actually do look through the procedure called the activation records, looking for a frame that has a handler that might want to handle this particular exception. If we don't find a frame-based handler, then we give the subsystem a chance if there was a subsystem port associated with the process when it was created. That gives the subsystem the ability to decide if it wants to have a different kind of exception handling mechanism. We may indeed give the subsystem a crack here also. We sort of don't know whether we want to. Originally we decided we didn't have to do that, but we may want to do that if the particular environment wants to have a completely different view of how exceptions work. Then we might want to look at the subsystem here too. In general, you never have a debugger port. You very seldom have a subsystem port, and you only look for frame-based handlers. If the subsystem passes, then we give the debugger a second chance. And this is kind of a useful thing. You know, you're trying to debug something, you get an exception, you say, well, on the first chance, I really don't care about it. We'll see if my program handles it. And if the program doesn't handle it, though, then what's going to happen is the system's going to handle it. The system's going to handle it. In general, what the system's going to do is say, like this. So you might want to have the debugger have a second chance at it. An exception handler can do one of three things. It can fix the problem and continue the execution. An example of that might be, I'll give you a couple examples. IEEE floating point might be an example where you actually want to get exceptions on some of the IEEE floating point operations, fix up the result, and continue operation in the program without ever interrupting it. Another case might be where you want to do something where you map a large part of the address space as no access, and you want to be able to take an access fault and say, oh yeah, I should map that in. Now I know it's there, and update cache information, or whether people with object-oriented databases seem like to do something like that. If you don't fix the problem, then you can say, I ain't interested, which effectively says continue the search. Or the other thing you can do is you can say, I want to unwind and sort of reset my context to a certain place. We provide extensions to both C and C++ for what we call structured exception handling. If you're familiar with Modula, I guess Modula Plus or some of the things that have been done there. Effectively, the syntax is, well, first of all, we're going to support the standard C++ syntax, which I think is try-catch, is the syntax. The C syntax we support is try, and then you have a guarded statement. And then you can say except, filter expression, and then this has exception handler. The semantics of this are, this is a compound. semantics are that I want to execute this particular set of statements. And if an exception occurs in that set of statements, I want to execute that filter expression. That filter expression is executed as a function. Within that function, you have access to local variables within the activation of this statement. It can decide what it would like to do. It can say that expression could be a function call that fixed up the exception. It could be a test to say, why did this exception occur, and decide whether or not it wanted to continue, handle, or whatever. Or it could say, I handle this exception, and what I want you to do is unwind back to my procedure activation frame and execute my exception clause. The other form, this is one form. The other form is you have try, and you have a guarded statement. And you say, finally, and you have a compound statement. And the semantics of this are that I want to try the execution of this. But no matter what happens and how I leave that execution, I must execute this. So for instance, suppose that you were in a function that called another function. In other words, in here, you had a function call. That function caused an exception, and that exception was caused by one of your ancestors. I'm sorry, handled by one of your ancestors. So we're going to unwind the activation frames. As we're unwinding the activation frames, we're going to find out that there was a call that went through a guarded statement here that has a termination handler associated with it. We will execute that compound statement in the context of the frame in which the guarded statement is. Now, this particular thing is very useful for doing things like deallocating resources when an exception occurs that will ripple through you. This form is sort of interesting where you sort of expect that an exception might occur and you want to be ready for it if it does. This finally is guaranteed to be executed if you fall through also. All right, so you always know it's going to be executed whether you exit this closing side of the brace here or whether you're unwound through. There is a way that you can tell within the filing statement whether or not you are being abnormally terminated. This turns out to be extremely convenient in writing the operating system, where basically what we do is we copy and verify that we're dealing with pointers that belong to the client. From then on, we have a copy of the pointer. From then on, we just go access his address space. And we do it within generally a guarded statement. And if he has some other thread running on another processor that's trying to delete that address space or change its access, the access to it, we don't have to care about that. We have to have no lock on his address space at all. Just go ahead and access it. And if we get a failure, then we say, I guess he changed this, and we appropriately can handle this, bubble it up. We don't have any routines like copy in, copy out. We don't deal with anything like that. And it's just very convenient to use this kind of thing.
I think you just turned up another term, reasonable architecture. And that is that client and kernel, user and kernel address space are uniformly addressable. That is, when you're running in kernel mode, your user space is addressable.
Actually, we assume that is part of a reasonable architecture.
Which is a reasonable assumption. I know I have an intimate experience with an exception to that assumption. But
yeah, I've dealt with a couple to the PDP-11 series of digital actually separated, the ones that ran protected and separated the user mode from kernel mode. Then they gave you these instructions, move to and from previous. Probably if in that sort of a situation, we'd still do the same thing. There's some what we call adaptation work required, all right, in the porting, as opposed to, you have to adapt the portable parts, right? And you would put in the appropriate functions that would copy the things, but you still would probably do them within the try-except constructs.
Yeah. You would have the function there rather than walk one of the references.
Right.
To be fair, you also uncovered another requirement here that the C compiler that we use to implement the operating system should implement these semantics. But it does make the operating a lot cleaner.
Well, it makes everything clean. We use this a lot.
The operating system is much cleaner.
We use this all over, even in user mode also.
You also mean that you have to have a compiler that supports frame-based procedure calls as well.
That's not absolutely true, as a matter of fact. I'm just going to get down to that. We've actually implemented this 3 different ways. And I guess it should be a fair continuum of what you can do. The 386 in the PC world is called roll your own calling sequence. The only calling sequence that must be a standard calling sequence is the one that crosses the boundary between the user and the system. That has to be one agreed upon calling sequence. But all other calling sequences aren't necessarily agreed upon. Generally, a particular compiler only generates one calling sequence unless it has some keyword that says, you know, this is a Fortran procedure. So what we do on the 386, 486 is we actually use a per thread list structure that is a LIFO list where we register and deregister handlers as you enter and leave procedures. And when an exception occurs, basically you look back up this list. The list has the information necessary to display variables within that frame. So that's kind of like one extreme. And actually it turns out in the 386, 486 we can implement that list without having to do any kind of interlocking on it. It's possible to do that because you know that it's absolutely LIFO unless you unwind, in which case if you unwind, you don't care. I mean, unwind peels things off the list, all right, because it takes handlers off the list. The second way that we implemented it was on a system where we had a formal frame definition for every procedure call. And we actually put the information in the frame itself about whether there was a handler, what its address was, and any registers that were saved or restored by this routine, and where they were in the frame. All right. And I might want to say one thing. What NT provides is it does the search and calls handlers. It does not provide the C structured handlers, exception handling. The C structured exception handling is provided by a handler provided by C that understands how to scope its own procedure, and that's it. So that's the second way. The third way that we've done it is on a machine that does not have a formal frame definition. It has a stack, or it implements a stack, and we've done it entirely table-based. So there's no active code at all. That particular one has the least amount of overhead as far, this is mixed, right, as far as procedure calls pay no overhead. All right, whereas in the other two cases, we actually pay some overhead on a procedure call to a function that uses exception handling. If you don't use exception handling, then you don't pay anything on the 386. You pay a little bit in the one that has the formal frame architecture. So there's 3 different ways that we've implemented this. Sort of, I don't know, experience is that the table-based one is by far the most efficient one. It's also by far the most fragile one. If the tables ain't right, it don't work. And dealing with a system where you're trying to do this at the same time that you're producing the linker and the stuff of the compilers is quite exciting. We talked about the process structure, and it was simple. say it's mock-like. I hope you don't call me on that because it's been a while since I really looked at mock. We have APIs that manipulate processes and threads. In general, the things in a system, you generally don't have the ability to do things across all thread objects or all process objects, but we have that. A process and thread object has a handle. There's a set of granted access rights to that handle. And a subsystem typically will create a process and a thread to run in that process and never give the thread or the thread the right to do an NT exit. All right, so it can't exit its thread. The only way it can exit its thread is to call the subsystem. And the subsystem then will say, terminate that thread. So you can get complete captive control over the threads and processes you create as a protected subsystem. We've designed it to be flexible enough that we think we can implement anything we know about, at least as far as process structures. There's no hierarchy, grouping, or relationship. The server subsystem provides all of that. We talked about access control, and we talked about the security profile being associated with the thread earlier.
So one quick question. One thing that Mock does a lot of is that there's a fair amount of inheritance going on when processes are created. You doing something similar?
Yeah. When you create an object, you get to say whether or not it's inheritable. And if it's inheritable, some objects are non-inheritable. If you create a process, you can't inherit the threads of the creator, for instance. So there are some objects that aren't inheritable. But in general, objects are inheritable. And you can decide whether or not you want things to be inherited. So you can get things like open file handles and all that sort of stuff inherited. There's the dupe operation. You can duplicate handles. And the other way that you can get access to handles or sort of objects in sort of an inheritance way is, suppose you had an environment subsystem that really wanted to have some other kind of fancy inheritance mechanism. Then there's this thing called superdupe, and superdupe lets you dupe handles across processes, and that's one of the access rights associated with the process.
Do you have any hardware dependency at all on your processes, like PSWs or?
No. Well, do we or don't we? We make an abstraction called a context record, right? And you, in general, should treat a context record as something that has some length, which is architecture dependent. It has some information in it that you have a pointer to that's passed to you every once in a while. And in general, what you do with this is you pass it back. You don't muck with it, right? And if you muck with it, then you are now architecture dependent. There are pieces of code that absolutely want to do this sort of thing. And go back to the IEEE example again. The floating point status that you see in general might not be the same across all processors. The PC is sort of the PC, and we sort of give you, we give you an address that's basically a P void that says this is an address, right? And it's 32 bits wide. We've tried to abstract the exception information that you're passed so that you're passed sort of generic kind of information and not the absolute bits that came out of the hardware. So things like the 386 and sort of together with the 386 and MIPS. MIPS only has effectively what you might call access violations, and that's read and write, whereas in the 386 you all have segment violations. So in the general exception architecture, there's a few bits in there that say, this was a segment violation, a segment limit violation. Well, you know, that bit just is never there when you're running on a MIPS machine. So we have made an attempt to do that, but yeah, you can get a dependency. If you start going and mucking with registers, if you're running a debugger, you sort of have a dependency on what the architecture is, although our debugger is pretty much independent of the architecture, other than that part that deals with the context. Displaying, storing, setting, getting, all that.
In your process management code, you talk
Yes. In fact, one of the things I haven't really said is how much stuff is architecture dependent, how much is architecture independent. And I would say that of all the portable code, probably 95% is architecture independent. There's maybe 3% that's written in C, but architecture dependent, and then there's maybe 2% that's written in assembler, that's definitely architecture dependent. And that's just, that's a swag. That isn't the absolute numbers, but that's about what it is.
Now, to say that again, 95% of the portable code is architecture independent.
Well, all the
90%
code
of
that's
the-
portable is architecture independent.
90% of the 5% of the code doesn't change, going
Doesn't
from one
change.
process to another.
Then there's
3%
3% that's written in C that does change, and then there's about 2% that's written in assembler that definitely changes.
We haven't counted it recently, but it's less, certainly going from one architecture to the other, you're changing less than 10,000 lines of code. So that's probably less than 5,000.
Oh, virtual memory. We sort of touched on this. Scored 4 gigabytes of virtual memory address space, that's 32 bits magically. We split it 2 gigabytes for the system and 2 for the user. On some processors, we wouldn't have to make that split. We could make it more for the user, more for the system. It turns out on MIPS systems, we have to make that split. We like to have the software run across a wide variety of systems, so we don't want people to write applications, for instance, that knows it has 3 gigabytes on one processor and 1 on another one. So we just split it right down the middle. Within the virtual address space of the system, on all of the implementations we have today, there's 8 megabytes of system-owned memory per process, and that's the piece of the virtual address space that we map the page table pages in. The page table pages always show up in the same part of the virtual address space in all processes, and we do that by having the page tables recursively map themselves. We support map files and paging, of course, from those, and that's fully coherent with the I/O system. You can open a file for read-write and in one process, and you can map the file read-write in another. You are looking at an identical view of the file, no matter what modifications you make. It's not synchronized. Any updates you make aren't automatically synchronized, and you have to coordinate that synchronization. But it's absolutely one copy. So we don't get into the case where you say, well, gee, somebody has this map, so you can't open it for read-write access, or vice versa.
That 8 megabyte of system of memory, that's borrowed out of 2 gigabytes of user address space?
No, it's out of the system's part of the address space.
Oh, okay. So that's a piece of system address space that switches to the side effect context switch.
Right.
Okay. Now I'm right.
Okay. I talked a little bit about processes being able, or one processor thread being able to read and write the virtual address space of another process. That's provided with some access rights in the process and also in the virtual memory. We do copy on write. We do guard pages. Guard pages are done for stack expansion. The way we do the virtual memory is it doesn't cost you anything to, I should say something about commit and reservation. Reservation says I want to reserve a set of virtual addresses. In other words, I don't want anything allocated there, I want them reserved. Commit means, hey, I really want something behind them now. So you can reserve a large stack for threads with almost no cost. And then we can dynamically expand it as the need be, and we do that with guard pages, and we actually do stack limit checking for each thread if they're going to allocate enough space on the stack so that it could possibly span over the guard page. And most of the time, this is a page or less. You don't ever go through a stack check. If you're allocating more than a page, then it's a few instructions. If you're allocating and you actually have to expand the stack, then the system actually expands the stack as you touch it and moves the guard page. We support multiple paging files. You can add paging files online. Paging, we page against the process, not the system. So we won't get into that debate. That's the way we do it.
Before you run away from this, your paging files treated very differently than your regular files?
Or what?
Your paging files.
No. They're just a file. They're not treated any differently than any other file. They're just a file on a disk. And when you make a page file available to use for paging, you look up the mapping information that maps virtual addresses to sectors on the disk. So I can't page that. And as you page in, allocate pages in that, or allocate from that file, then you just page directly into the file. So there's no special operations for paging. There are some interfaces that are exported by the I/O system to help memory management do paging. It helps memory management build I/O requests without going through an MT read or write file. It just submits its I/O request directly down through the layered driver architecture. The I/O system.
Why, by the way, did you not do a read or write? Why did you decide to do IRPs and pass them around? For pure efficiency or for actual problems?
I'm not sure what you're referring to.
You said that your virtual memory system uses some routines exported by the file system to do this paging business, paging files.
Right.
You said that what they do it though is they create an IRP and then they pass that straight to the file system.
Right.
Now, I understand why that works, but I'm still curious about it, since you said earlier that various boxes in your executive can call the API, why you decided to build an IRP.
You don't want to traverse the whole thing of translate this handle, check this access against granted access, generate an IRP.
It's okay, I want you to understand that. I was just trying to make sure it was only efficiency as opposed to another reason.
No, that's the main reason.
There also might be an issue lurking there that if you know you're doing a full page size transfer, you can optimize out a whole bunch of checks that have to handle arbitrary amount of transfers.
Yeah, I don't know, let's see. We talked about all driver code written in higher level language. We don't have one single driver that's written in assembler, not one. The only thing that we have that's written in assembler is on the 386, it has I/O instructions and memory mapped I/O. So some I/O you can do by direct accessing a device registers, but some I/O you have to do through port instructions, which are in and out instructions. So those are implemented by a subroutine, which of course is written in assembler. That's it. Nothing else is written in assembler. We have multiple installable file systems with automatic volume mounting and verification, which is something that's needed in the PC world. Basically, as an installable file system, you register yourself with the system. When you're loaded, you say, you know, I'm me. Anytime that you get a request for a volume to recognize the volume, call me. I may know what it is. So the I/O system then, if you say you want to open a file, the I/O system will say, geez, there's no volume mounted here. Is this direct access to the storage media? If the answer is yes, then it will see if you have access rights to the storage media directly. If you don't, or you are going after a file within that, then it will say, geez, is there a volume mounted here? And if there is, it'll say, fine, it just passes a request to the file system that's mounted the volume. If there isn't one, then it starts calling file systems, asking them to recognize what this volume is. This is sort of grown out of a requirement to not have to have a mount and dismount command, but at some point we might have mount and dismount commands that execute some things that might absolutely work differently than this does. This is so we can recognize media in the PC world, what it is, without, because PC users don't know what mount and dismount mean. The driver architecture is layered. I said something about that before. We support the I/O semantics of multiple operating systems, at least these three. It's hard to say that we would implement the semantics of everything, but with the semantics that we have in our I/O system today, we can do these three.
Question going back to the two items. What sort of restrictions are you under for PC users not understanding dismount? I mean, in some other worlds, the fact that you're a dismount operation means that you can play games with memory and media states being out of sync.
Yeah. Well, if you dismount something, and what will happen is, if you dismount something and something else gets mounted there, then when you come back again with your original request, we'll notice that it's different. Right? We have to deal with this with floppies, where people are used to putting
Yes, that's
the
exactly
floppy
what I'm
in.
thinking of. What happens if somebody pulls a floppy out of the drive at exactly the wrong moment? What kind of guarantees do you have to make so that the stuff in the floppy is what the user thinks is there?
Actually, in terms of the way the floppies are done on the PCs, we can't really guarantee that because there's no. We can guarantee that we won't mistake the media for something else. In other words, you put in a floppy and you open a file and you read it. You pull out that floppy, put in another file and open another file and read it. And now you try to write the original file, right? We will absolutely notify this and tell you, hey, the wrong floppy is in there, right? But as far as you yanking something in the middle of a transfer, we can't guarantee that. We can guarantee. Let's see. What can we? We can guarantee that we can report the error if there was a transfer going on, but we can't guarantee that everything was kosher, right?
Right.
You won't lose the file structure because of the way that the floppy file structure is done, because everything's up to date. Indeed, we won't cache. We will cache floppies, but we will only cache them right through. We won't cache them right back, right? In fact, there's something I probably ought to mention is that you can decide whether or not you want your file accesses to be cached. And there's also the capability in the I/O system to say any cached information that you have. Well, first of all, you can say whether it's cached or not. You can also say what the cache policy is, whether it's going to be right through or right back. And if it's right back, then you have another primitive that says, I want you to make sure that everything that I've written is written back. Yeah, it runs MP. We support both synchronous and asynchronous I/O. If you open a file and say you want to do synchronous I/O to it, then we will maintain the file pointer for you. However, we also allow you to do the operation of seek and write if you want to, even on a synchronous file that's been open for synchronous I/O. The reason you would like to do that a lot of times is to avoid the synchronization that you have to do at the user level if you're doing multi-threaded I/O, where a seek, a read or write could be separated by another thread doing a seek and a read or write. So you can do seek and read, seek and write. The file addresses are 64 bits, so we're not going to run out of addressability in the file system for a while.
When you say you've got support for I/O semantics for multiple operating systems, do you
What that means is it means that we can map the semantics of those systems directly into the semantics of NT.
What I mean by the question is, do you have a small level of a small number of very low-level primitives that you then expect the server to provide the full body of the semantics, or do you have a rich, full set of semantics which the server can map something down onto?
We have a rich set of semantics with the goal of always being able to map the I/O semantics in the client DLL and not have to go to the server.
Okay.
If we were to have a sort of a philosophy that we go to the server for I/O, then we would have had a much simpler I/O system. But it still has to implement all of the protection semantics and security semantics, because that's where the secure, trusted computer base is.
What's the difference, a terabyte?
Pardon?
What's that, a terabyte?
I don't know. The only other name I know up there is femto, and I think femto is 1,000 times that, or 1,000 times a tera.
Because what you have,
So I don't know.
you have 10 million terabytes of addressable file space. Give or take.
16.
Okay, well,
Oh,
you
it's more than
you
that.
have 8
More than
million
that.
terabytes.
Huh?
30
30 bits.
billion terabytes.
30 bits is a billion, right? 10 more bits, a terabyte.
It's 8, 10 into the 18. I'm just curious what happens. You have 8 million terabytes of addressable.
You and I will be dead. Even if we're counting bits, you and I will be dead.
Is your virtual memory system only 32 bits?
Yep.
How do you support mapping of large files?
You can, we will, I said, out of the 32 bits, we'll give 2 gigabytes to the user, part of the address space, and we'll give 2 gigabytes.
That's a convention for
Right.
2 kilobytes.
You can map anything up to 2 gigabytes. All right? The way that you map things is you map windows of them. So you map a window into a file, a view. It's called mapping a view of a file into your address space. And you can map as big a view as you got address space to map. Well, it's bigger than physical memory.
How hard is that 32-bit limit for virtual memory? Lots of things can break into 64 bits.
Well, 64 bits is an interesting problem because the whole C language breaks when you go to 64 bits, and you try to supply the backward level compatibility so that you can just compile the old sources and they run, because there's sort of this implicit built-in knowledge that, geez, you know, pointers have a certain size and you can typecast them and do operations on them. The way that we are approaching this is that, you know, when we go to 64 bits, we will absolutely do a new kernel. So everything that runs in privilege mode will be 64 bits. However, it will export a 32-bit compatibility subset that says you can run the old stuff constrained to 32 bits of address space, binary, or you can upgrade those and run them 64 bits.
You said you'll make a new kernel, but you really meant you'll make a new kernel in executive.
Right. Yeah, actually, that's general. In fact, it's mostly more a new executive.
This, of course, assumes some sort of appropriate language and compile support for distinguishing 64 from 32 bits.
Yep. The other thing that's a real problem, too, is that things get passed around and stored in structures that are 32-bit pointers, and that becomes a problem, too.
So the MIPS advertisement that says 32 to 64 almost for free is not quite right, man.
I'll tell you what. The day before MIPS delivers a 64-bit version of Unix, we will deliver a 64-bit version of NT. How's that?
Well, I think the claim is that if you have the chip in 64-bit mode, you can still run 32-bit apps or something like that. But that doesn't
No. You run in 32. If you run in 64-bit mode, then we're talking about a new executive.
Or, you know, the operating system.
Right, the operating system's new. But yeah, that's exactly what I said about having the philosophy that what we would do is we would run the old binaries,
right,
and if you wanted to upgrade, then you would probably make some source changes. You don't want to take that bet?
I believe you.
Okay.
I was in bed on 2 days.
2 days?
You're right.
Say a few things about the cache manager. We sort of talked about the cache manager a little bit indirectly. We have one central cache manager that does all file caching in the system. No device drivers do file caching, all right, or disk caching. We have one cache manager. All our file systems use it. The LAN manager redirector uses it. Our LAN manager server uses it. It's fully integrated with virtual memory. We talked about coherency. The cache manager competes for real memory through the virtual memory system. And that means that when your system is fairly idle, you can have lots of things in the cache. But as you get more activity on your system, there's more demand for real memory, and the space for the cache manager shrinks. So when you got lots of memory, you can have lots of memory for the cache. When there's not a lot of memory available, then you're actually competing for the virtual memory of the system.
Do you use some of the sprite algorithms to do that at all, or?
We don't use some of the sprite algorithms, but if you want to supply them, we'll be happy to look in.
Anything one more about it?
We talked about coherency. Cache manager doesn't compromise the file system security. We have automatic read ahead, write back, lazy write or write through, which we talked about through the cache manager. There's both synchronous and asynchronous operations through the cache manager. There's kind of three ways that a client deals with the cache manager. You can do what's called buffered I/O in and out of the cache manager, where you actually have the data. You either have the data in a buffer, you want to transfer it into the cache, or the data's in the cache and you want to transfer it out of the cache. Or you can say, this is BYOB. You can bring your own buffers and say, I want you to DMA this into or out of my buffer. I'm sorry, you can ask the cache manager to DMA, not DMA, you can say, see what you do. You ask the cache manager for the buffer, and then the DMA goes in and out of that buffer directly, and then that buffer would eventually get mapped to the user's address space. And the other thing you can do with the cache manager is you can pin buffers in the cache so that if you're a file system that's implementing some kind of an esoteric metastructure on the disk that has a complicated update policy, you can basically pin everything, get everything updated, and then unpin it and do the write, which makes it a lot simpler to update in a coherent fashion. The last one is kind of a novel thing that's done. What happens is the metadata on the disk isn't necessarily in a file structure, but the cache manager makes it look like it's a file structure so that it itself can use the cache manager to cache the metadata. One last thing here is sort of has a bad name. This is called PE, which is our executable image format. This is a little different than the PC structures, PC executables we used before, and it's a little different than the Unix world where COF is used. The intent of this structure is that it will be